All right, so we're going to go through just a couple of theorems quick. I would suggest to write these down to have them in your notes, so you can be referring to them as you review, because remember, you'll have notes when you take the AP exam if you needed to reference something quick, and you would want things organized in a nice way. So maybe start a page where you just start to put little theorems and any notes that you would want to be able to just check quick. So I probably won't talk as long enough for you to be able to write it down while I'm talking. So if you need to write it down, pause it, write it down, and then you can listen to what I say. But mean value theorem, f has to be continuous on the closed interval, differentiable on the open. Then there's a value c. So c is an x value, where the derivative at that value is equal to the slope between the endpoints. So in other words, the instantaneous rate of change is equal to the average rate of change. So if you have some curve, say you're finding the slope between the endpoints, that slope is guaranteed to match at least one tangent line. In the picture I drew, it was in two tangent lines, but you're guaranteed at least one. So that's the mean value theorem. Another theorem, and both these theorems you saw with Mr. DeLange last year. Rules theorem, if f is continuous on the closed interval and differentiable on the open interval a, b, and then there's a third condition, f of a has to equal f of b, then you're guaranteed that there's some x value in the interval where f prime of c is equal to 0. So again, maybe here's a and here's b. If the y values of those are equal, we're guaranteed there's at least one spot, and again, the one that I just drew had two spots, but we're guaranteed there's at least one spot. There must be a turning point, so the slope must be 0. So again, for that, if you want to pause that, write that down all the way, that'd probably be a good idea. Third theorem is the intermediate value theorem. So if f is continuous on a closed interval, then for any number in between the y values of the endpoints, we're guaranteed there's some x value that would give us that y value. So let's say we've got this interval here. We are guaranteed for any y value in between the y values of the endpoints, there's some x value that would hit that. And a common application of that is you have some function. One y value endpoint is positive, the other is negative, so then we're guaranteed by the intermediate value theorem that somewhere in between there must be a 0. So again, pause it if you want to write down a little more. And the last thing for this short video is our setup for Euler's method. So Euler's method allows us to use tangent line approximation to make little jumps to then approximate where the function would be. So you'd usually start out at some point. Let's say you were starting out at 1, 2. Let's say they had dy over dx. They told us was equal to 2, let's say 2x over y, we'll call it. And our step we wanted to do, it's usually something small, and we'll say it's like 0.1. Well, we sub our x and our y in here, so sub 1 on top, 2 on the bottom, we'll get 1 for our dy over dx. So then we do that times the delta x, which would give us 0.1, and then that's what we add on to our new y value. So this is a bad example because the numbers are going to be the same. So this 0.1 here, we added on to the 2.1. Now this is always going to go by 0.1s because of our step that we have. So now what you'd have to do is you'd sub the 2.1 and the 1.1 in for those to get the dy over dx, multiply it by 0.1, and I guess I should have showed here that we were doing 1 times 0.1 to give us 0.1. Get your dy over dx, whatever you get, you'd multiply it by 0.1, see what you get, and that is what you would then apply to get the next y value. Okay, so that's just a quick refresher on Euler's method.